Okay, looking at situations involving numerical methods, and let's say we have a differential equation whereupon we have dy over dx is equal to x plus y, and we have a given initial condition whereupon y naught is equal to 1. And we're looking at finding out, okay, just what y01 is going to be equal to with using the Euler as well as the improved Euler methods. And if you notice for this table, okay, we have with the Euler method with the step size at 0.1, and also with the same method with the step size at 0.005. And we have the improved Euler where we have the step size is equal to 0.1. And now, if you notice in this table, we have the actual y value rounded to the nearest 4 places. And in terms of how to go about the number of steps for the step sizes of 0.1 and 0.005, there is an item in Maple, okay, that we have, again, for the number of steps. And that is going to be taking the ratio of the final and initial x values divided by the step size. So in the case of what we have in this particular layout, okay, so you have with the initial conditions, so you have y naught is equal to 1, so we have x of 1 is equal to 0, and we have with 1.0, okay, our final destination value, we have x of 2 is equal to 1. And so for the number of steps involved, okay, if h is equal to 0.1, okay, so we're looking at 1 minus 0 over 0.1. So you have 1 over 1/10. So you're going to have 10 steps, but for a step size of 0.05. Okay, so for the number of steps in this one, okay, so we have 1 all over 0.005, and you will have considerably more steps, and that is going to be at 200. Okay, so we have working with the Euler method with the step size at 0.1 for this differential equation. And okay, so you want to start out with this opening statement to be able to perform numerical methods with Maple. So we have with, open parenthesis, students, and then you have open bracket with numerical analysis, followed by close bracket, close parenthesis, and then we have colon. And once you press enter, you're ready to perform numerical methods. Okay, and so for the Euler method, okay, so just attaining from the palette, okay, we have d over dx of y of x, and you have to stress the independent variable whenever you're looking at dy over dx, you're looking at y with respect to x, and we have is equal to x plus, and again, not just x plus y, but x plus y of x. And we have for the initial condition, okay, we have y naught is equal to 1, and after this, we're looking at the upper limit, okay, to which x is going to arrive at. So we're going from x equals 0 to x is equal to 1, and with the step size at 10, okay, stressing that the step size is 0.1, and looking at what we have once we get to x is equal to 1, your approximated y of 1 value, okay, is going to be at 3.187. Okay, if you notice at 3.187, and the table had more decimal places. And let's say that if we want to add to the number of digits here, okay, we can do this. Okay, so you have num steps is equal to 10, and if you have digits, and we'll say we have take out to, let's say, the 10 digits. Okay, so this is going to be a fuller display of what we have here. Now, in the case of looking at putting this in tabular form, if I want to establish a table, okay, so you got the same command, okay, and I again, number of steps, you have 10. That's for the step size of 0.1. And I can control the number of digits on display, so I had 10 digits. And say if I want to look at the tabular format, okay, so we have output is equal to information, and we have upon entering, and so okay, if you notice, you have x at 0, 0.1, 0.2, 0.3, 0.4, 0.5, all the way out to 0.8. And if I want to go all the way out to 1.0, if you notice in the context bar, I can go to show all, and this is what we have in the display. So this is what you have for the Euler output. Okay, and again, we had earlier 3.18748.492. And so this is what we have here. And this is Maple's numeric solution. And the rightmost column, okay, is going to be the size of the error. Now, let's say that for what we have in terms of the command. Okay, so with the number of steps, okay, so if I have this at 200 steps with the step size at 0.005, and I'll carry this out to 10 digits, and I'll go ahead and put this in tabular format. Okay, so I have output is equal to information, and we have upon entering, and you notice, okay, we have a very small step size, and we have quite a way to go to get out to x is equal to 1. And if I zoom out just a bit, and then we have showing all, and this is what we have at the bottom. So you have quite a few steps in the mix. Okay, so you have with the Euler method next to the last column on the right, and so we have 3.42303, and this is Maple's numeric solution, and notice we have the error size is substantially smaller. Okay, so reverting back to what we have with the Euler method, and I'm going to transition over to the improved Euler. Okay, so just kind of going back to whenever we had the step size to be at 0.1. Okay, so we had this particular display. Now, if I go from the Euler to the improved Euler, now for the improved Euler, now your opening is not going to be with Euler. It is going to be KUTTA. Okay, but we're not looking at the KUTTA method right yet. And what is going to happen is that for the new twist, okay, what's going to, other than changing Euler to KUTTA in the statement, I'm going to have with the changeover, okay, not only am I going to change from Euler to KUTTA, but I'm going to have a sub-method to signify that we have the improved Euler, and that is going to be referred to as the Heun method, H-E-U-N. And I believe that is named after a mathematician whose last name is Heun. And if we display the output, okay, and we have upon pressing enter, and the KUTTA Heun, again, that is the improved Euler. And if I just show all, and we have on display. Okay, so this is what we have with the improved Euler. So we have 3.4281616, and again, sized up against Maple's numeric solution, and we have an even smaller error with the step size at 0.1 in comparison to what we have with Euler's 200 steps. Like the smaller the step size, the greater the accuracy. Well, the improved Euler in comparison to what we have for the Euler, okay, is quite a marked improvement in this particular case. But not all numerical methods will converge upon a stable solution. And I will give you a case in just a moment, and we're going to cross over to the KUTTA method. Okay, now in the case of numerical methods, okay, and we do have from page 458 that there are certain equations where you're going to have the numerical methods will not be quite so successful as what we have had in previous encounters. And just want to mention something about the KUTTA. Okay, so you had this table of outcomes, and Now, if you notice, we have with this table of values, we got x at 0.4, 0.8, 1.2, and so on. And let's say that if you were to see if we can get these outputs in accordance with what we have here in Maple. Okay, so again, we have with the initial x value. Okay, so you have x of 1 is equal to 0, and we have with the final x value, okay, we have x of 2 is equal to 4. And in terms of the number of steps, say for what we have in the case of the step size at 0.2, so we're looking at 4 minus 0. And we have all over the step size, so we have at 0.2. 4 over 0.2, that's going to be 20. And for the step size that we have is 0.1, well, that's going to be 4 over 0.1. So that is equal to 40. And of course, with the step size at 0.05. Okay, so we keep taking half the step size. So that's going to be doubling the number of steps. And so that is going to come out to 80. And looking at how you can get these numbers to appear, not only with the final output, but for the in-between stages. Okay, so just starting out, again, you want the opening command to have, okay, with student numerical analysis, and for the RUNGE KUTTA method. Now, when we had the improved Euler, the sub-method was the Heun method, Heun. But now with this version of the RUNGE KUTTA, again, we have with the equation. So from your palette, you have d over dx of y of x. And again, whenever you're entering y, while x is the independent variable, you're going to stress y of x. So you have d over dx of y of x is equal to 5 times y of x minus 6 times. And if you don't use the palette for the natural logarithmic base, you can just type in exp, and we have of negative x. Again, the initial condition we have y naught is equal to 1, and we're going out to x is equal to 4. And now we're going to have for the number of steps, okay, that is going to be 20. Now for the RUNGE KUTTA method, the sub-method is going to be RK4. And we can say that for the output, we'll say that the number of digits will be 6. And we'll go ahead and put what we have, setting up a table. So you have output is equal to information. And upon pressing enter, okay, so we're going from 0 to 4. And notice, okay, we have kind of cropped out, okay, have 1.6. And if we go ahead and show everything, okay, so we go 0.2 at a time. And for what we have for the RUNGE KUTTA, okay, so you have 103, 127, and again, so you have, notice you have a very high substantial error size, because this is Maple's numeric solution, and look at the size of the error. Okay, so this is, needless to say, a disaster. So there are limitations with the RUNGE KUTTA method, and for what we have, if we go out to where we have the step size at 0.1, so you have the number of steps to be at 40. And for what we have in this particular case, we have for the output, okay, so you have not as large an error size, but still way too much. And if I double the number of steps even further, so going out to 80 steps with a step size at 0.05, and we have for the output, and just showing all, and we have in this particular case, you have the error size small, but you got 631.055 for the integral error size, okay, and that is by far way too much. But anyway, so you got Euler and you got the improved Euler, where you have RUNGE KUTTA with the sub-method Heun, And you have the RUNGE KUTTA method where you have the opening statement is RUNGE KUTTA, and whereupon we have that the sub method is going to be RK4.